We keep circling back to this basic power series because it's a really simple series where we have an equal to 1. So our an value here, an just is always equal to 1. And we have this nice function 1 over 1 minus x. And we've been doing some substitutions and rearrangements of this. So that's what we're going to do here. We're going to start with that same function. We're going to plug in at negative x into the x there, and we end up with the function 1 over 1 plus x. And then we can do the expansion. We can expand out that series, and we get 1 minus x plus x squared minus x cubed, etc. in that pattern. And we know that as long as we keep x between negative 1 and 1, we know that geometric series will converge. So we have now established this by some substitution. Okay, we're just substituting again into that basic power series. And we're going to generate a new function by integrating this. So if we start with the 1 over 1 plus x and integrate it, we're going to end up with the function log of 1 plus x. So if we integrate the series then, so this we have integral of 1 over 1 plus x, and we integrate the series, which is equivalent to 1 minus x plus x squared minus x cubed. If we integrate the series, we're going to get a series that represents the integral of that function. So if we integrate the function, we get log of 1 plus x. If I integrate this series, I'm going to get the series that represents that log of 1 plus x. And not only that, I can integrate the generalization. I don't have to do it term by term. And I'm going to get the generalized series the generalized formula for the series that will calculate the log of 1 plus x. So this converges for the interval negative 1 to positive 1 when we start with 1 over 1 plus x. So when we integrate this, this will also work for the same interval. So this series, whether we have it in the expanded form or in the generalized form, it will converge for the interval negative 1 to 1. So basically what's happening then is this series that we've now generated, okay, this series negative 1 to the power n, so it's alternating, and we just increase the power by 1 and divide by that same power, we get this expansion here. That series is going to mimic the ln of 1 plus x function in the interval that we've been given. So we can, if you want to know what this looks like, it looks like this. So we have our log of 1 plus x, that's the green function. And as we expand out the series, we get different polynomial terms. So we get an x, that's just going to be a linear function, minus x squared over 2, that's a quadratic, plus x cubed over 3, that becomes a cubic. And what I've drawn is minus x to the power 4 over 4. So that polynomial expansion of 4 terms is going to look like that dotted line that I've drawn there. And notice that that dotted line mimics a function in the interval from negative 1 to 1. And the closer I am to the center, the better the approximation, or the better that the fourth degree function mimics the log function. So we can then use that expansion, the polynomial function, to estimate values of log. And that's kind of nice because it's really hard to calculate log with plus and times. But now we have this polynomial function that we could use to calculate it. So if I want to find the log of 1.5, log of 1.5 is equal to log 1 plus, and we're going to let x equal 0.5. So we put 0.5 into the log function, which means we can put 0.5 into our series function. So we get 0.5 minus 0.5 squared over 2 plus 0.5 cubed over 3 minus 0.5 to the power of 4 over 4 and dot dot dot. We could keep going, but we're just going to use the first four terms to do our calculation. And hopefully that is going to be pretty close. And if you take a look at the graph of that, near 0.5, when I take a look at the graph, near 0.5, those two graphs are very close together. Okay, those two graphs are very close together. So we should expect a pretty good approximation based on that polynomial. So as I do the calculations for the polynomial, when I type this all into the calculator, I'm going to end up with 0.401, 0.416, and it looks like it just repeats after that. Okay, so that's my approximation of log of 1.5 using the polynomial. The actual value and again, if I put this into the calculator, all the calculator is actually doing is just using the same calculation, series calculation, but they're just going to use way more terms because a calculator is able to do that. But if I put it in the calculator, I end up with 0.4054651. And you can see that it does start to diverge in the third decimal place, but it's pretty close. And we can see that the one that we estimated in the red graph, okay, is a little bit below the one that we estimate, that the actual graph of log, which is in green. And that makes sense. So up to now, we've been just kind of using the basic power series function and its variations, and we've been now integrating and differentiating to generate new functions. But we can take this another step further.